Mulcahy, and this is my talk, Machine Learning for Games. How many people went to the Machine Learning for Games talk yesterday? Show of hands. Handful of people. So it turns out that me and Professor Landon just completely randomly submitted talks with the same title, no association. Reached out to him on LinkedIn, so I got to know him, so it's kind of cool. But anyway, this is my talk, Machine Learning for Games, so hopefully, if you saw it yesterday, it'll be a little bit different, and if you're new, it'll be something, new for you as well. So a little bit about me. I am basically a web developer. I've been, I worked at Yelp, worked at OAC. Currently, I'm a team lead at Overdrive, where I work on Libby, which is a cool app. You can download library books for free from your library. I'm not a professional game developer, but I originally got into programming through game development about 15 years ago. So I've worked on a lot of games, had a lot of fun with it. And then last 2 years, I got really into machine learning. So I've been doing machine learning for 5-7 years, somewhere in there. And I started a nonprofit group along with some of my co-founders called Cleveland AI, which is basically help educate the community on machine learning for free. So we run study groups and those kind of things. So if you're from Cleveland, definitely come check out our group. But that's enough about me, so let's get into my talk. So here's what we're going to talk about. We're going to go over a very brief history of what I'm calling games for machine learning. And then we'll go into what is machine learning for games, which is where I think we should be going. We'll go through some mainstream examples of what I'm talking about. And then we'll get into some algorithms on how you can do it yourself. I'll do a demo of a game I've been working on this past year. And then if we have extra time at the end, I'll go through kind of the 3 key components you need to do machine learning in games. So a little bit of history. So machine learning was started in like the 60s, and people have been studying AI for a very long time. One of the first earliest big victories for AI was when IBM's Deep Blue supercomputer played Garry Kasparov, who was the best chess player in the world at the time. They played a series of 7 matches with Deep Blue coming out on top. And at the time, Garry Kasparov thought that IBM was cheating because their machine was so good and was so creative that he figured humans had to be giving the computer secretly moves behind the scenes. So already in the late 90s, AI is better than humans. But there's no machine learning. So basically the developers at IBM, they handcrafted this, and how can we actually learn to play games better than humans from the games themselves? So that took another 20 years, basically. Google worked on a program called AlphaGo, which is to play a game called Go. If you're not familiar with it, basically you have these stones that you put down on the board, and you try to capture areas to control, and you get points based on how much area you have. So you can look that the number of moves on a Go board is way higher than the number of moves on a chess board. So people thought that computers can never beat Go. There's just too many moves. They can never be better than humans. Well, it turns out they were wrong, because in 2016, one of the best players at the time, he got beat by Google's AlphaGo. And what they did was they actually had a system that played against itself, and it learned how to play Go from just play testing against itself. So this is kind of one of the first games where machine learning was used to beat the game. Then, just a few short years later, OpenAI, which is another huge AI machine learning business, they went and they played Dota 2, which is a kind of real-time strategy style game. You control characters with spells and abilities. If the average game of Go, you played maybe 500 moves, the average game of Dota, you have to make 40,000 decisions by the end of the game. So you're making way more decisions than you are in Go. And yet machine learning comes out on top and defeats the best team at Dota 2. So it's just, machine learning is getting better and better. Then just very recently, Google played StarCraft 2, which is very similar to Dota 2, but instead of controlling one unit on a map, you control a whole army. And each one of the units in your army can move independently, use its own abilities. So I have no idea the estimate, but there's like tons of decisions, tons of moves to make. So AlphaStar, Google's algorithm, was able to beat Mana, who's one of the top players. And he didn't win a single game against the AI. He came in all excited, all cocky, and he just got completely shut down. So what is the message that we're getting at this point in time, right? It's like AI defeats humans, it keeps defeating humans. I really don't like where this is going, you know? It's like, this is not what I signed up for. So that's what I call games for machine learning. It's like, how can we make machine learning better using games? So, all right, there's a little bit of a silver lining, kind of. We can have machine learning, systems that we trained in Dota 2 play alongside humans. So that sounds great. You're like, I could play with, if I don't have 5 friends, I can like have AI bots that play alongside me. Or if you're like at work, maybe all your coworkers will be machine learning systems one day. So I don't know, maybe it's not so great. But so what are like games, machine learning for games? So Unity has, like many people probably use Unity, it's one of the biggest game engines. In 2018, they worked on this open source system called ML Agents, which is basically, it's like a plugin library you can use in Unity to train agents using reinforcement learning, doing the same algorithms that Google used to beat StarCraft 2, etc. So the one thing that is a big problem with ML agents is I think it has to do with Unity's kind of market position. They're on top of the game development market, and they're looking to get into other markets. So last few years, like they're trying to get people to use Unity to build movies or to do architecture in Unity. And now they're kind of marketing this ML agents library as something that if you're an AI researcher, you can use Unity to build better algorithms. It's not really built for game developers. It's not super game developer friendly. You have to run Python alongside your C#. It's just kind of a big mess. So I'm not super happy with ML agents, but we can get into what we should be doing. So can we go beyond what ML agents is trying to do? With these systems like the StarCraft, Dota 2, all of the machine learning happens before the playing of the game. Basically, they run on like this huge supercomputing cluster, playing like thousands of years of gameplay, and then they just take the output of that and they use it to play the game. The machine learning is not actually involved at all in the game itself. Also, like, it's not really interacting with humans. Like, it's just bots playing against bots. They have some examples, like to start that StarCraft 2 system, they actually trained on ladder replays of the humans playing first, to like bootstrap the machine learning, and then eventually had it play against itself. But like, humans aren't really in the loop at all. So kind of the challenge here is, can we build games where humans can directly train the AI instead? Can we make the machine learning part of the game? I think so. So here's some kind of mainstream examples of where people are trying to make this work. So many people have played Smash Bros. You maybe played here in the tournament. And Smash Bros. Has these amiibos where you can basically train a character in the game using like your playing. There's a problem though, that it's kind of not real machine learning. What it does is it basically learns if you're in like this situation and you always like up kick, then I'm always gonna up kick. It doesn't learn this like unique strategy of I try to like box people out and I try to do this, like whatever. It just learns like simple, this is the situation, this is what I do. It can't learn combos, etc. So it's like a step in the right direction, but we can do better. Another mainstream example, the Forza series for a number of years has had these drivatars, I think they're called, where basically you can train a virtual driver to drive similar to how you drive. So if you take turns really tight, or if you like speed really fast around turns, it can kind of learn these little intricacies of your style of playing, and then build a virtual character that plays the game like you. The thing though is there's still something a little fishy going on here, because you can play against like a low-level version of yourself and like a high-level version of yourself. So they're kind of blending like other players' online abilities with your actual training. So it's still a little fishy. And then we have this game that came out earlier this year. It's called Well True Learn. It's one of the first games I've seen that's like very close to trying to do machine learning. So in this game, you play as a machine learning engineer, and you have like a super smart cat that apparently is an expert in AI. And what you do is you build a translator that translates meows to English, and then your cat like teaches you about machine learning, and you somehow become like an expert. Unfortunately though, you don't really do real machine learning in this game. You basically connect like nodes and edges into this graph, and you sort out like shapes, and the shapes need to end up in the right buckets, etc. It kind of teaches you machine learning and the AI like history through like these little pop-ups, but you're not really doing any machine learning. So far I've been like pretty disappointed. So I decided that I was gonna learn how to do this and try to make my own games that do this. My vision of what it should be. So that's why I'm sad. There's no real machine learning. So, all right, I assume most of you don't know what machine learning is. If you do, you're just gonna have to bear with me. So, basically, if you don't know, this is how it works. You put in some floating point numbers, some magic happens in the box, and floating point numbers come out on the other side. You can't really explain how it works. So, but a little bit more seriously, neural networks are like the most cutting edge thing. People have been doing them since like probably the 60s again. In 2012, people figured out how to train like these really deep networks. So that's what deep learning is. It's just a fancier version of neural networks. So you have these layers and they're connected, and I don't know, there's some magic. How does it really work? It's just a bunch of matrices. You're just multiplying numbers together, you're adding numbers together. It's just math. There's just a bunch of math. So just remember, it's just magic, all right? So let's take a look at some algorithms. How can you take this magic technology that can put out the right floating point numbers and use it to actually do stuff? So there's 3 different algorithms I want to look at. Reinforcement learning, which was a big part of Professor Landon's talk yesterday, and then 2 other algorithms that I think are a little bit closer to what we should be doing. So learning from human preferences, which is like a slight tweak to reinforcement learning, and then imitation learning, which is what my demos use. So how does reinforcement learning work? Basically, there's 2 things. You have the agent, which is like your character in the game. Could be like a robot or an animal, whatever it is. That's the character in the game. And then you have the environment, which is basically everything that's not the character. And the character takes actions in the environment, and then the environment changes states. So if I like moved, then maybe nothing changed, but if I like shot a fireball, maybe like the wall blew up or something. So the state of the world is changing as I'm taking actions. And then the environment is also passing rewards to me. So if something bad happens, like I get a negative reward, and if something good happens, I get a positive reward. And then I, as the agent, let's say I'm trying to maximize my rewards so that I get as much positive reward as possible. So this is where I started out. In late last year, I built this really simple game using ML agents. It's not very fun at all, and you'll see why. But basically what you're trying to do is, there's these little robots here, and they're trying to push this ball into the center of this pit. And if the ball ends up in the pit, then it gets a positive reward of like 1 point, let's say. And then if the robot goes into the pit, it gets a negative reward. It basically like dies. And every step of the simulation, it gets like a very small negative reward to encourage it to like get to the ball and win as fast as possible. So this is basically like the full reinforcement learning problem. Everything like, if you can solve this problem, you can technically like use reinforcement learning to solve like any complicated game. So you can kind of see here that like Unity has a really big overhead. It's hard to run like a bunch of instances of Unity on your computer. So what you do is you actually train a bunch of the robots in one Unity executable, and they're all kind of running side by side in their own different mini world, and then they share their intelligence. So like maybe this one over here, it's taking like random actions in the beginning, and then it accidentally knocks the ball into the pit. And then all of a sudden, all the robots know, like, oh, we got to get the ball in the pit. That's how we win this game. So like they all help each other learn, and that's how they get better. So what are the problems, though, with reinforcement learning? One, it's super slow. This simulation on my home computer, which has got a pretty decent graphics card, in order for them to learn to like push the ball in the pit like pretty regularly, it took 2 hours of running like in a headless mode without the graphics, just running in the background as fast as possible. And you can see that there's like 30 of them. So it basically took like 60 hours of playing this game in order to learn how to play it. And it's that simple. So it's super slow. Like you can't imagine a player like waiting 60 hours in your game for something interesting to happen, right? So that's, I don't know, kind of rules it out. It's not like interactive. Like I have described to you a simulation, not a game, right? Like where's the fun? All I do is just watch it happen. It's kind of interesting, but it's not really any gameplay. And then it's not personal. Every single person that watches the simulation is going to get the exact same thing in the end. Like it's just going to be a robot that knocks the ball in the pit. Nothing special there. So how can we like tweak this to make it more interesting? Well, reinforcement learning does have this one part that's gameable. We could change the reward function based on what you as a player likes. So maybe like one player wants the ball to go in the pit, so they'll give that a positive reward. Another player likes to see the robot die, so they give that a positive reward. So there's like maybe a little bit we could game this type of setup. And there's an interesting algorithm that OpenAI put together that demonstrates this. So let me show you that. So if you haven't been in machine learning, OpenAI publishes this blog, hence the name Open. Like everything that they're doing is out in the open. You can learn all you want about machine learning. And they have this really simple game where your character is just this like leg with a foot. And the normal goal of the game is you're just supposed to try to run to the right as fast as possible and as far as possible in like a limited amount of time. But they wanted to show that you can train this game to do anything. So they actually wanted to train this leg to do like a backflip. And the reason this is kind of interesting is because it's really hard to describe like how to do a backflip. So if I was to like someone, let's say I met someone and they never heard of a backflip before, and I'm like, oh, you jump up and then you like spin. And it's really hard to describe like a detailed algorithm for how you do a backflip. It's easier to just do a demonstration, right? Like I can't do a backflip, but if I could, I would just show you, and then you would know how to do it. Or there's an alternative. You could just keep doing random stuff. And if it kind of looked like a backflip, I would say, yeah, that was good. Like, keep trying to do that. And eventually you would figure it out. So how do you do that? Well, they basically built Tinder for machine learning algorithms. So, all right. So we got some feet here, right? And they don't know how to do anything. So it shows you two versions that are kind of based on our current version. Like, let's make a new version and see which one is better. Like, we'll let you pick. Which one's closer to what you want it to do? So you just keep voting left or right, and then slowly it gets closer to doing a backflip. So they wanted to show that this would work with anybody. So they did an experiment where they found like 20 random people off the street, and they gave them this game, and they wanted to see how long would it take for them to be able to train the backflip. And would people even succeed? So it turns out that the average person that did this was able to do it in 900 steps. So basically they voted left or right 900 times. So that's kind of a lot as a game developer, but if you like compare it to what you hear in the news, right? Like when you think of machine learning, you usually think of big data, like we need to have billions of images, we need like people going on Facebook, like clicking their faces or whatever. Like we need a lot of data to make machine learning work. Well, it turns out with only 900 data points, they're actually able to do something kind of interesting. So maybe change your expectations about what you can do with this. So, and then if you're interested, you can read more, but basically what they do is your human feedback trains this reward function, and then you do the normal machine learning, reinforcement learning loop I just described to you earlier. So when I saw this paper in like early last year, I was like, I gotta start working on this. Like I can see the potential here for something really fun. But I think we can go even further. So, imitation learning. This is like the final algorithm I want to talk to you guys about. So, basically with imitation learning, we're going to do like the monkey see, monkey do type thing. One player is going to, like the actual human player, is going to be the coach to the robot. It's going to directly teach the robot how to play the game. So, how does a normal human play a game? Well, what they do is they look at the screen, they see some pixels, they make some decision in their head, then they push buttons on the controller, and that updates the state of the game. And then they kind of go around that loop over and over as time goes on. So what we can do as the game developer is we can feed that same information to a machine learning algorithm. We basically take the state of the game and feed it to the AI, and then we take the inputs that the player made and we feed that to the AI as well. And the machine learning algorithm can then learn the connection between what is in the world and what the player is doing, and can basically become a copy of you. So eventually, once it knows the connection between those two things, we can hand essentially the AI its own controller and just say like, hey, you play alongside of me. Now you've basically trained like clones or like teammates that are copies of yourself. And the thing that's cool is you don't have to train just like one AI. You could train a bunch of these. So let's say we're playing some kind of fantasy game where there's warriors and healers and stuff. I could essentially play the game as a warrior, play through all that, save that character off, then play through the game as a healer, save that off, play through the game as a spellcaster, save that off. Then I could go online and play against other people with my team that are all just like copies of me as the player. That's kind of interesting, I think. So here's my demo. I've been working on this for 2-ish months, so I don't have fancy graphics, but I hope it will spark your imagination on what we can do with machine learning. So I have this set up in kind of a debug mode to explain how it works, but you control these robots. So we got blue robots and green robots. I can take control of a robot, and then it's a little hard to see, but it's doing ray casting from the center of the robot. So the robot is seeing basically stuff in the world around it. So this ray goes out, it hits this wall, and it tells the robot there's a wall here, and it's that far away from you. And then these are a little bit lighter color, so the robot sees like there's a building here, and it's that far away from you. And then you can see these red lines for the red enemies. It's the same thing. There's an enemy this far away from you. So then, what you can do is you can start collecting data. So I'm just going to drive in circles around the base to tell my teammates I want them to drive in circles. Kind of ignoring the whole point of the game right now, which is to protect my castle from these enemies. But, so what's happening right now is basically what I described to you. It's telling, oh, they're getting stuck over there. It's telling them that whenever you're in this situation where these walls are this far away from you or there's enemies near you, do this thing. Do what the player is doing. So the AI can only learn what you've shown it. So I built a system where basically when they get stuck in corners and stuff, you just switch to that character and show it what to do. And then they can learn how to get out of that situation. So you can also train them to shoot and stuff. So ideally what we'll do is we'll train these blue guys to defend the base, and then the green ones will become my attack squad to go fight off where these enemies are coming from. So we'll drive around here, and once I'm kind of satisfied with their ability to fight the red enemies, I can switch over to one of the green guys and we can go figure out where the enemies are coming from. So this is kind of the idea of like training the warriors versus training maybe like defenders. So here's this like base where enemies pop out every 30 seconds or whatever. I can go train all these guys to go off to battle. So the ones that ended up here in the corner, they don't know how to get out of the corner. You have to show them how to get out. And as soon as you show them, you can see that other guy is just following along with me because he knows what to do now. The ones that are stuck in this corner over here, you just gotta show them how to get out of the corner. So hopefully you can kind of see the potential of being able to build this game, maybe similar to, for this I was kind of going for like an RTS kind of vibe where it's like defend over here, but attack over here. But I'm thinking about building something similar to like Pikmin, where you have like these squads and you're like Captain Olimar and you bring your like robots with you and you go solve puzzles, fight enemies, that kind of thing. So, last bit here too, you can see up in the corner there's this like graph with like a waveform in it. That's basically the result of training. So that shows you if the data you're feeding the robots, they're actually able to learn from it. If the line goes really high, that means they're not learning. And if it's really low, that means they're like learning exactly what you're doing. So that's kind of like the debug mode I have going here. So then let me show you a more updated demo. So there's one problem with that version I just showed you, and that's the rays themselves. When you are a player, right, and you're like making a decision, you might be over here, like shooting at a guy over here, but if there is like a wall and all the rays are hitting the wall, then this robot can't know to go fight something like over there. So I wanted to make it so that the robots could have a better version of seeing similar to how you see as a player. So I built out this grid system. So instead of doing rays, what happens is every single one of these grid cells reports what is in the grid. So you can see here these white dots say that there's like an ally in this grid location. These orange dots show that there's a building there. And if I go up to like an enemy or a wall, you can see that there's red dots and black dots for the wall. So what's happening then is like we take this information, turn it into floating point numbers through a little bit of magic, feed it to our neural network. It spits out floating point numbers that we then translate back into the controls on the controller. So it's all just a little bit of magic, but depending on how you choose to set things up, you can get vastly different results. And you can see like this version, I don't have shooting working. I like broke it somehow, so I gotta get that back in there. It's not very exciting. But yeah, this can just kind of show you like there's a lot of different ways to do this and a lot of things to explore right now. So back here, so there's three things you have to figure out as your game developer in order to train a machine learning algorithm. The first thing is you got to figure out how are you going to take the state of the game and turn it into data, turn it into those floating point numbers that you're going to feed to the neural network. Then you have to choose what's going to be inside that black box. So at this point in time, you can't pretend it's just a magic black box. You actually have to go inside there and figure out how you want it to be set up. And then finally, you have to choose a loss function, which is basically like how does your network get feedback. So we talked about like that reward in the reinforcement learning. The loss is basically the reward. So in my game, the loss is just an untrained version. So they take like a random action, and I take a certain action, and we just compare like how far are those apart. Eventually, when the machine learning algorithm gets closer and closer and closer to what I did, the loss gets lower and lower and lower, meaning it's not getting a negative reward. So for perception, right, you have a lot of choices. It's usually a good idea to have it be localized to your character, because then you can drop that character into a new environment and it'll still work. So like, I call it omniscience, which is when like the AI can just know stuff about the world. So in my game, like let's say the base has like this health bar. All of the robots could just know that the base was losing health. So they could be off on some far part of the map and then just like magically know, like, oh no, the base is getting attacked, and then run back to the base to defend it. You can do other things too, where like we're feeding in the locations of enemies on the map. The problem though is that when you're giving a demonstration to the robot, it's making the connection between when there's enemies far out in the world, I need to take these actions. And if that exact situation isn't happening in your game at the moment you're playing it, then they'll just be taking random actions. They won't be learning that connection. So it's a bad idea to have omniscience. Instead, it's good to have this kind of localized data. So that's kind of why we have these two different approaches. So then you have to figure out your model architecture. So with a neural network, you have to figure out like how many layers are in your network, how many neurons are going to be in each layer. For my game, there's basically like 7 layers, and each network has, I think, like 500 neurons in it. So it's doing a lot of matrix math in order to make this work. And then besides that, you have to determine like how are these connections going to be between the neurons. If it's this really simple version where everything is just connected to everything, that's called a feed-forward network. So with this version here where it's feed-forward has no recollection of time. It doesn't know what happened like a moment before it or like what's going to happen in the future. It just knows like right now at this moment, there are enemies in front of me, like I need to fight them. If you wanted to include time, you would have to use something called a recurrent neural network, where basically you would feed it not only one input layer, but you'd feed it like what happened the previous game frame, what happened the game frame before that, etc. And then it can learn the connection like over time. If I shoot at enemies, then they die. So, and then finally there's some other things like convolutional networks, which is how this grid works. It learns like patterns in the grid. It doesn't just treat everything as being unrelated to everything else. So with the convolution network, it's able to learn like this grid cell and this grid cell are next to each other, etc. Versus with that ray version, all of the rays are kind of treated equally. They're not near each other or whatever. And then finally, you can do other approaches like meta learning, which I won't get into, but it just sounds really cool. It's learning how to learn. So you're being, a little bit meta. Like you're trying to train a network that actually knows how to learn in new situations. So theoretically, it can handle situations that, you haven't really shown it recently. And then finally, there's like these loss functions. So the loss function is usually what determines like what type of learning you're doing. So imitation learning is like a fancy way of saying supervised learning, which is where you have the player directly training the robot, and you're doing that like distance calculation I just described. You can also do things that are a little bit more creative. So we can actually train 2 neural networks, which is how Gale works. You basically train one neural network that plays the game, and you train another neural network that can tell whether the actions, so basically you feed it actions from the neural network and from you directly as a player. And then you ask that second network you trained, did these actions come from me or did they come from the robot? So it learns how to be a critic. Basically it says like, that came from the neural network, that came from the human, like this data came from the neural network, that came from the human. And eventually it becomes a system to give rewards back to your gameplay network. And then finally you can do something like direct policy learning, which is instead of the player like giving demonstrations and then the network training on that, it's more like that Tinder type game where you see some behavior and then you give feedback to the network saying like, don't do that, like that was bad, do this, that was good. And then we already talked about reinforcement learning. So, I'm super excited about machine learning. If you're interested in this as well, I'm starting a company called Strife AI. We're gonna try to make machine learning and AI part of games. So we got like 10 minutes for questions.
Have you been exploring on AWS and any of the things they have on there?
So I'm like familiar with what they do. Since I use Unity and like monogame, I'm more of a C# person, so I use like what's available in Azure. The problem with what AWS and Azure and like Google Cloud give you is they give you like very canned stuff. Like this thing is good at detecting images. Like, is there a face in this image or whatever? They don't give you like more cutting edge things. So if you want to do something new, you can't really use what's available out in AWS.
Wouldn't it be better to play the game, the computer play itself, to learn, so you could be faster?
Yep. So that's actually an approach you can do is similar to what the StarCraft 2 did. You can actually have the AI train off of the player's data at first to kind of get it started. And then once it's in a good place, you can let it play against itself in order to collect more data. So you can switch from basically doing supervised learning to doing reinforcement learning.
Is it possible to kind of pre-program the AI at all to do any specific functions, or does it have to start from zero and learn from the player?
No, so I didn't really go into how the neural networks work, but under the hood, they're doing like that matrix math. And those matrices start out filled with random numbers, and when it's learning, it's actually just learning what numbers to put in that matrix. What you can then do is you can just save off those numbers to like a file and then just load them back into the game at a later point in time.
Yeah.
Do you think with machine learning and AI, you can make more complex NPCs?
I think so eventually. Like right now what I showed you is pretty primitive, like they can drive and they can shoot. We could do an approach where basically you save off the weights and you have characters in your game that are already saved in there that have been trained with a neural network. So they might have more interesting behaviors and they might be a little bit less predictable than like a programmed NPC with like a state machine or something like that. So I think we could make more interesting NPCs.
Would it be maybe possible or better to use a mix between that ray tracing and the grid to help the computer learn, or can you only do one at a time because of the way you have it set up?
You can do literally like anything. If you can just if you can turn it into a floating point number, you can do it. The problem though is like sometimes it can be hard to, so I showed you like that loss function. Sometimes it can be hard for the network to make the connection between like what you're doing and what it's seeing. So if you like feed it too much data, or if the data is like unrelated, like obviously if I fed the network like data from like just a bunch of zeros and then I was like, play the game, it like wouldn't be able to learn the connection between the data I fed it and the actions it took. So you have to be smart about how you choose the data. The other thing too is the more data you feed it, the slower that training is gonna get. So it's not gonna be something you can do in real time like I'm doing here in the game. It might be something you had to do like offline with like a loading bar or something like that. So those are kind of the limitations.
Okay, so obviously this is a tool that can empower a lot of emergent NPC behavior in games, but also recognizing that emergent behavior is a two-edged banana in a sense, because emergent behavior makes the game more interesting for the player, but also makes it more interesting for the test team.
Yeah.
So have you looked at how this kind of technology might be used to improve testing and testability, even of games where the AIs might not necessarily be emergent, but like multiplayer games where you can't really predict player actions when the players permute their actions with a lot of people involved? Has this been applied at all to the testability and finding the edge, beyond there's the usual finding the edge cases and testing those in individual tests? kind of a more holistic testing.
Yeah, so do you mean testing, like testing out the gameplay itself, or what do you mean?
I mean, looking for, places, I mean, any kind of an MMO, for example, players figure out, even without cheat mods or anything like that,
Oh.
players find things that the developers didn't anticipate, that this stack of perks combined with this weapon lets a player jump
Yep.
75 meters in the air.
Yeah, so I don't know if there's any way to like auto-detect that that's happening, but the people that were training neural networks in StarCraft 2, they actually found strategies that pro players who'd been playing the game for years had like never known about. So like in StarCraft 2, you like put workers on the mineral field and you like collect minerals, and like the game suggests to you like put 24 workers, because if you put more, it's not worth it. There's like diminishing returns. And the neural network would always load up its like mineral fields with like 30 or 40 workers, and it would always win. And then players, like actual human players, started doing that on the ladder, and they started winning more than players that weren't doing that. So like the neural network was able to like test out and find new features of the game, sort of like the meta game, I guess you could say.
Yeah, so curious about the kind of the resource taken by incorporating a neural network versus just a traditional behavior tree. So if we're going to train NTC or like your potential AI teammates, like would that be more memory like intensive or like processing intensive than just have like a preset behavioral tree and just be there?
Yeah.
What are your thoughts about that?
Yeah, so basically like in almost any case, like the neural network is going to be the most like CPU and memory like hungry compared to like any other machine learning algorithm. Basically, like in order to update those like weights inside, you have to keep track of like the derivative and like the gradient of this like magic function that the neural network is learning, and it has to maintain that like through the game while it's doing the training. So it can get like very memory intensive. The benefit though is that like the architecture is such that it can kind of learn like anything. If you set it up right, like give it the right inputs and the right outputs, it can learn like any behavior, versus maybe like with a behavior tree, it might be kind of like pigeonholed into doing certain behaviors. I'm not sure. I haven't really experimented with it, but that's just kind of my thought there.
I have kind of a related question. It seems like with all this matrix math and stuff, you could do some hardware acceleration. And I'm wondering if you were using like the graphics card to do stuff and you could now have millions and millions of calculations going on, what kind of benefits would you get from that sort of scaling? Like if you had millions of nodes in your neural network, what would that allow you to do that you couldn't otherwise?
Yeah, so that's actually how, the technology I'm using to make this work is Google's TensorFlow, which is like a library for doing matrix multiplication essentially, where the matrices might be more than two-dimensional, they might be like n-dimensional matrices. So like in my game itself, like the actual training is using like 5-dimensional matrices. So when you get like these really big matrices, you can like batch them up. Like I'm gonna take all the training from the last like minute or whatever, and you can put that on the GPU and run it like super fast. The problem though is like, there's a trade-off, right? Because you have to do the I/O to get it to the GPU. So if your batch size isn't big enough, you end up not actually getting any benefit. It ends up like not being faster. So most neural networks, like in production, they actually use like a CPU version of TensorFlow. They don't use the GPU version. It might be possible in this game, like we collect a ton of data points, we make these huge batches, put them off on the GPU, and then we do like the Indiana Jones approach where we like swap out the neural network you have with like the one from the GPU. So that might work, something like that.
I'm sorry if this is a super simple question because you kind of skipped over something that I found totally fascinating earlier. In my field is not AI, but you said something about, at the very beginning when you did the ball game, about getting computers to, they wanted points. You get them to earn points. And my question was, how do you tell a computer to want something, being points or whatever? Or maybe a different way of asking the question is, how do you impose meaningful consequences on something that doesn't have a self?
Yeah, so the way it works is actually just through like math. So you're taking the derivative, which if you like, if you've taken calculus or whatever, basically you have this reward function, and you're saying like, I want to get this reward to be like positive infinity or whatever. So if you have like a function that's curling up, you just take the gradient of that and you can say like the steepest slope is going this way. And then that's just how it learns, I guess. So it's just trying to take like that reward function and trying to like maximize it or minimize it depending on how you set it up. I think we're out of time, but if you have more questions, I'm happy to take them here in the hallway or whatever. But thanks a lot for listening to my talk.